There we go.
This month is long, Bob. What do you choose?
It generally does. So this is Module 1, Section 5, Chapter 1, Section 5, depending on how you want to look at it. EXP is a fancy way of writing an exponential function. For instance, you can write it this way. You know, f of x equals e to the x, the natural-based exponential function. But you also could write it this way. And a lot of computer programs would rather take the function that way, because then you don't have to raise to a power of. So EXPx is the same thing as e raised to the x. Does that make kind of weird sense? It took me a while to get used to that with computer language algebra systems, that you had to write EXP instead of e caret x. It understood this one, it did not understand the other one. Yay! Another student.
The other one's coming too.
Oh good, yeah. More surprising.
I got stuck at the train tracks.
Alright, so this is just word problems basically that involve logarithms and exponentials. Generally they concentrate on the exponential part of things. There's only a few problems that you can use logs as a function and have word problems associated with it. Usually they're Richter scale or pH scale are those types. Alright, so let's deal with something we talked about before. And I said I would come back to it. Well, I'm coming back to it. They talk about this, I think, in the second section. It might be the third, but well, actually, no. First section, exponential functions. So this would, if you go back to the first section, you'll see what I'm going to do to this today. Of course, I'm going to give explanation of why it works. We noticed when we did this formula that if we fixed a, p, and t, and messed around with n and made it bigger and bigger, that it started approaching a specific value. Remember that? And we also came up with this little formula. The definition of where e comes from, the natural number. And what I want to do is take these two formulas and shove them together. In other words, I want to change the formula on the left to have an e involved in it. Remember what LIM represents?
Limit.
Limit. So basically it's saying take n and shoot it off to a really, really big number, and then go even further than that. So the first step is to try to force this piece to look like this piece. We're going to do a little manipulation to force it to look like. Now they both have 1 plus, so we're pretty good on the 1 plus part. So the messed up part is this r over n. I should use n over there, because I don't want to get messed up with this n and that n. Let's call that k. It's easy to change. K. K. Oh, and then over here, k. There. I don't want to get messed up with the n on the left and the variable on the right. Alright, so if I can force r over n to look more like 1 over k, an individual number, it would be really nice. So, a lot of people don't like doing this. Let's take a fraction, 2/3. How do I write that fraction as 1 over a number? Okay, if you don't know how to do that, if you don't know what this number is supposed to be, what can you call it? X. Solve for x. How would you solve for x? Cross multiply, so you get 2x is equal to 3, and therefore x has to equal
3 over 2.
3 over 2. So if I take 2/3 and I shove it in the bottom of a fraction, it's the reciprocal. Because to get a fraction out of the bottom of a fraction, you have to multiply by its reciprocal. So it's just kind of reversing the order. So the first step is to take this r over n and shove it in the bottom of a fraction. So it becomes p, parentheses, 1 plus 1 over what?
N over R.
N over R, the reciprocal. And that's going to be raised to the nt. Okay. So now I have it set up so I have 1 plus 1 over a number raised to a power. Now, so they're still a little bit messed up. N over R is still too many variables. It needs to be a single variable k. So what you can do is let k equal N over R. Why not? Algebra is beautiful. Replacing numbers with letters. Or replacing more letters with letters. So let k equal N over R. I think this will work. Well, if k is equal to N over R, my question then is, what's N equal to?
Wait, what?
If I let k equal N over R, what's N equal to in terms of k?
K times R.
K times R. This is what's called a double substitution. I'm actually going to use it for the inside and also for the outside. And my goal really is this. My goal is actually to have these k's in place of this formula over here. So I want to get rid of this piece in the bottom and the exponent up top and have a k involved in both of them. All right, so if I let k equal N over R, this turns into P parentheses 1 plus 1 over k, because k takes the place of N over R, raised to the, what takes the place of N?
Okay.
KR. So we're going to get KR times,
T.
don't forget the T from up above. All right, so now we got it to this. Getting closer. So here's your 1 plus 1 over k, 1 plus 1 over k, raised to the k, what's kind of in the way? RT. So we go back to basic algebra. If I have a raised to the xy, I can write that a different way, right? I can write it as a to the x. Nope, because then it would be x plus y.
Plus a to the y.
But then it's plus a to the y, and it's really not true.
Oh, put the y on the outside.
Put y on the outside. Power to a power, you multiply. So if they're multiplied together, that means you can rip them apart as power to a power. So I can write this as p parentheses 1 plus 1 over k raised to the k, and then take that whole chunk and raise it to the RT. So far, so good. You know, power to a power multiplied, it would all go back to the beginning. This piece in the middle, this chunk, is exactly the same as this piece up here. So if I take the limit of it as k goes to infinity, what does that blue chunk equal? E. It equals E. So if I let k go off to infinity, this thing equals P, B, R, T. Whatever's in that blue box will turn into E all by itself, and then whatever's left over is the P in the front and raise the RT in the back end. So if we use this function, f of t is equal to pert, I call it pert. It's the only way I remembered it. Shampoo, pert. When I had hair, I used to wash it. And my parents always bought the shampoo pert because it had conditioner and soap in one container. It was the first one to do that.
Yeah,
This
that shit's
becomes a
like-
function known as exponential growth. In other words, if you start with a population of p, and you know the population rate of growth, you can find out how much your population is growing in a certain period of time. PERT. So, for example, Maybe I should start off with something easier than this.
Right, yeah, probably.
Nah, we'll trudge ahead. I think we can figure it out. A population doubles every 5 hours. And starts with 100. Kind of like a bacteria. You know, they grow pretty quickly. You probably wouldn't even notice if there was bacteria growing on a piece of bread, mold, whatnot, until it gets large enough. And once it gets large enough, boy, that sucker takes off. You know, you might have a little spot of mold on your bread one day, and the next day the whole slice is covered. It grows pretty quickly. All right, so a population doubles every 5 hours, and it starts with 100. How many after 1 day? 24 hours. How many would we expect in this population? Now, there's 2 ways of doing this, but I'm going to do it with PERT. You can also do it with 2 raised to a power. That one also works, but PERT is a nice constant. So if I have f of t equals PERT, I'll show you the book formula a little bit later. Do I know anything about this problem?
Mm-hmm.
What do I know?
It starts with 100.
Where would I put that?
P.
P. So 100 goes in for P. E doesn't ever change, so it'll be times E.
The rate.
Do I know the rate?
5 hours.
That's not a rate though. 5 hours is a time.
Doubles,
yeah.
so 2.
Hmm?
2. 2's and doubles.
So that becomes,
Wait,
if a population doubles and it starts at 100,
what? 200.
200, where would I put the 200?
Rate. R.
It's not a rate. Rate is like miles per hour. Where would my 200 go? I start off with 100 and I end up with 200.
Oh, on the F of T.
Of the other side, over here, right? So we replace f of t. It's the population after a period of time. All right. What about r? Do I know r? And I keep saying, heck no, because rates are per something. Do I know time?
5 hours.
5 hours. So here I'm going to go 5r. You have to have at least one letter left over so you can solve for it. So how would we solve for r?
First, you divide by 100.
Divide both sides by 100. If you do that, the other side becomes 2. You'll find that when you say double, you'll get a 2 on that side. If you say half, you'll get a half on that side. It's kind of a neat idea. Equals, what's left over?
E to the 5.
E to the 5r. Okay.
Take ln of both sides.
ln both sides, so you're going to get the ln of 2 is equal to
5R.
5r, because ln and e will cancel. I shouldn't say cancel. Poof. And you get 5r. And solve for r, you just divide by 5. So r is approximately what? It's exactly ln of 2 over 5. But what is it approximately? Ah, she brought her calculator today. We're so proud of her.
0.1386.
0.1386? 0.1386. 13.86% per hour. That's pretty big. Imagine if you had a loan for that much. That's how loan sharks would love to work. If a loan shark charges you 1% per day, how much are they charging you APR?
God knows, I took that class with you
I
like
know,
5
you
years
should know
ago.
this. If you get charged 1% per day, what's your APR? APR is annual percentage rate.
365.
365%. 365%. Even though it sounds small for 1% per day, it's quite big. Am I done with this problem? Have I answered the question?
No.
No. So you start all over again, plug in what you know. You have a function, f of t. P is equal to 100. That doesn't change. P is a constant.
Don't you know F of T too?
Well, that's what I'm coming up. No. That's what we're trying to find. How many after a day? F of t is going to tell you how many. Your function is e to the, what else is held constant?
The rate.
The rate, 0.1386 t. So this becomes your function that describes the population of this bacteria or
I thought
whatever
you
it
knew
is.
T.
I knew T for this first part. The only thing that T told me in this first part is it gave me R. T changes. T is your variable. It could be short or it could be long. R is fixed. Whatever T you choose, R will be fixed. And that 100 up front will also be fixed. So what do we need to do? If I want to find out how many after a day.
I thought you would put it where T is.
I do. So
Oh.
what am I trying to find? F of 24. So you put 24 in here. Whatever goes in for T, you replace it everywhere. 100 E 0.1386 times 24. And you type that in your calculator. Remember to use second ln. That it breaks my calculator.
Hold on, how do you type this in the calculator? What do you put for A?
Second ln. So you're going to type in 100 second ln
Why do I have to hit second?
to get the blue lettering in your calculator.
What?
Well, in your case, yellow lettering.
That's
you look
E
at
to
ln.
the X.
Yeah, that's what you want.
Okay.
Because it says e to the
Gotcha.
0.1386. Oops. 86 times 24 in parentheses. Oh, it's not as many as I thought it would be. Unless I typed it in wrong. Yeah. How many would you expect at the end of the day?
2,783.79.
Well, if it's 0.79 and you're counting these individually, you round it to the nearest whole. Here's 10. It won't kill you though. All right. 1. What is rate? 2. How many people were living in Hawaii?
Wire as in W-E-R-E.
Fine, you English people.
Math teacher, not English teacher.
He was trying to be an English teacher earlier.
1965. Little vocabulary. Since this problem starts in 1945 and the other date it gives you is today, which is 2015. Since this number is between those two, this is called an interpolation. Interpolation. In between. Now, if I went beyond 2015 to like 2020, that's called extrapolation. Extrapolation. Fancy words. So one is inter and the other one is extra.
Is this where you count the years from?
Well, you have to find out how many years, yeah.
Well, this is finding the projected population in 1965.
Between two numbers. It's a little different than guessing how much beyond.
Oh, yeah.
Between two numbers is actually a better estimate. Beyond is a worse estimate. If that makes any sense. Because you don't really know what's happening in the future, but you can check out what
in
happened
between
in
is
between.
in between's a better guess.
Yeah,
A better guess.
better guess than beyond.
Yeah.
Estimate is
Yes.
guessing. It's fancy. So what would t equal in this case? Oh, I'm sorry. Well, I'm sorry. What would t equal in the first question? If I'm trying to find the rate, what time am I looking between?
70 years.
Is it 70 years?
45,
60, 70, yeah, 70 years. It's been 70 years since the end of World War II. Kind of scary. All right, I'm just curious, how many years until 65 then? Just 20. All right, so how do I find the rate? wow, that messed up horribly.
So tell them what you do.
That's crazy. Oh, so how do I find the rate? Perp. So you start off with f of t is equal to perp. And you plug in what you know. What do I know?
That the population was the 207,000.
So I can put in 207,000 here. A lot of different ways you could do that. But E 70R equals, on the other side, do I write 2.5? Since I wrote this one as 270,000, I have to come over here and go 2.5 million. Now the biggest mistake with big numbers is either adding an extra zero or leaving a zero off. So be really careful you count your zeros. Use commas to group them. That's how I suggest. All right, what would be the first step? It almost looks like 7 over. What would be the first step of solving?
Divide by 207,000.
All right, so if you divide both sides by 207,000, you're going to get something ugly.
So what are you doing dividing by 207?
Yeah, move this to the other side, the 207,000. Is it 12.077? I'll write the whole thing. 12.077. E to the 70R. And then the process starts becoming exactly the same, just kind of repetitive. What do you do?
Does that say 12.077?
Yeah.
Your handwriting
Glasses,
sucks.
Emily?
No, your handwriting's horrible.
You can sit right there. My handwriting isn't that horrible.
I have contacts in.
They're not doing you well then. So what do I do to both sides? To get to R?
LM.
ln both sides. So this becomes ln of 12.077 equals
70R.
70R. And divide both sides by 70, and you're going to get R is equal to
0.035.
0.035. So it's about 3.5% population growth per year based on the population of the year. Think of it that way. All right, so that gives me the rate, R equals 0.35. The next question is, how many people will be living in Hawaii in 1965? So you start over again with your function,
Wait,
f of t.
Its rate is
It's 0.035.
0.035.
36.
0.35.
Oh, dear.
36.
0.035. There we go.
36. If you want to be correct, it's 36.
She's such a precise.
Just saying.
What's after the 5?
5.
0.036.
Man.
Let's be precise here.
I mean, why not?
6. I want you to be. Actually, I'd rather you go 4 decimal places, but that's just me. Equals, what's the next number?
The 207,000.
The 207,000. E to the 0.036 times 20. You can type that in your calculator, and that should give you the population approximately in 1965, if things grew nice and exponentially. A lot of ifs there.
Which they did. Which they did.
What?
There was a lot of people. There was a time where a lot of people left Hawaii
It's really expensive.
at a time where.
Yeah, populations are always fluctuating, so this really only works if you have like an island of certain resources. We'll talk about that in a second. So, what's this answer?
425,267.67.
Okay, cool. Whole people, we can't cut them.
Yes, I was gonna say.
Yeah.
Whole people, we
There
can't
was
cut them in
fractions
half.
of people there.
The average household is 2.5 kids.
Oh, I didn't even look at the
2 whole
problem
kids and
we're actually trying
half
to
a
get.
person. All right. So this works really well for, actually it works better for bacteria than it does for the human population. But there's a problem with it. There's a what do you call it? Paradox. Very dangerous paradox. If you have a population that starts off with this population and it grows exponentially, as time goes off to infinity, what's happening to this population?
It's increasing
How far?
forever.
Forever, to infinity.
Right.
It's impossible for a population to go towards infinity. So if we set up one of these where the rate of growth, I saw a problem in one book. If the Greek gods had one child per century, what would their population be over 2,000 years? And the answer was outrageously huge. And then, of course, their population would go off to infinity, even though they didn't have that many kids. So what happens with real populations?
They level up.
They level off. What forces that?
Death.
Death doesn't actually do that. This formula over here accounts for death. That rate, the R part of it, is actually related to, it's called beta minus delta. Beta representing, take a guess, births, and delta representing deaths. If this number is positive, your population is going up. If this number turns negative, like there's more deaths than there are births, like the Black Plague, the population is going to go down, and so forth and so on. So the rate actually includes both births and deaths. What else would force a population to stabilize? Do you remember Easter Island? Have you ever heard of Easter Island? Does anybody live there? Easter Island, you know the big statues that stare out at the ocean? Don't you watch like Nova or anything like that?
I don't watch what?
Okay.
Nova? Never mind.
Yeah, I was about to say, ever seen Night at the Museum?
What?
She's just so closeted.
They're really big statues of just
Faces. A very long face that stares out at the ocean.
Gotcha.
Alright, so they had this island, it's off of South America, and it was discovered, and when they found it, there was absolutely nobody there except all these big statues were staring out at the ocean. So someone had to live there before. So where'd they all go?
They died.
Why?
They ran out of resources.
They ran out of resources.
Leveling of the plane.
Leveling of the plane. So what happens is, if you put a bunch of flies in a jar, and you put an apple in there, eventually the flies are going to consume the entire apple, and their population is going to go
Down.
down.
They'll die.
So if you live on an island, you don't want to use up all your resources, you want to do what's called sustainability. So what they did is, because of those statues, they cut down a bunch of trees to roll those statues out to the ocean and put them up. After they cut down all the trees, when the rain came, it washed away all the good soil and they couldn't plant any plants anymore. And therefore their population healed. Now what normally happens with a population is you have a maximum population. The amount of resources you have, the amount of food and land and all the things that you need to live, there's a way of figuring out what your maximum population is. And if you have a population down here and it starts at P, it's going to start growing exponentially for a little while, but eventually it's going to reach a point where the growth actually turns into a slower growth. Where the left hand is like a exponential growth, the other side is like a logarithmic function in a weird way. Alright, so you get this little S figure. Where is the human race right now on planet Earth? Population-wise. Anybody know?
8 billion?
6.
I can find out.
Oh no, it's more than 6.
7 billion the last time I knew. Let's see if Siri knows. What is the population of the world? Let me think.
Let me think. Here's what I found on the web for what is the population of the world.
Oh, that's a good one. It's coming. Hopefully it works on a cell phone. It might not. Okay, there it is. The world population is 7.2 billion. 7.2 billion. So we're right about here. They estimate the world population, the largest it can get without going through all the resources and then taking that dive like Easter Island did, is about 10 billion. How close are we?
Very
Too close.
Way too close. Very dangerously close. The closer we get to that little dotted line, things are going to get really bad in the world. People will start fighting over water. You know, there used to be oil. They'll be fighting over water, land, arable land, you know, stuff you can farm on.
Yep.
But we're
What's
ahead.
nice about being a farmer's daughter.
Oh, dear Lord. And to complicate that, you have global warming, which makes even the arable land that used to be arable, not arable anymore. Where there used to be water, there is no water. Where there used to be ice, there is no ice. So a lot of things are changing, so that might actually suddenly drop, which is also kind of interesting.
Will you give me a little sheet of paper with the homework on it so I can go and copy that down?
I'll take a picture of it and send it to you. Check your email. Radioactive decay.
Half-lives.
Half-lives.
Damn, get ready to go.
That's fine. Send me an email, I'll send you a picture. So I
You're
don't know.
gonna send me an email.
You're gonna send me an email. I'm gonna send you a picture.
Okay. I'll log on for the first time.
Wouldn't that be nice? Alright, so what does it mean to be a half-life?
Logarithmic function, right?
I forget what the half-life of uranium-238 is. I think it's like 70,000 years. Let's just make it 70 years. So if you start off with 200 kilograms of this stuff, after 70 years,
See you Friday.
how much are you going to be left with? 100. After 140 years, how much are you going to be left with?
50.
50. After another 70 years, 210 years, you'll be left with
25.
25 kilograms, not grams, and so forth and so on. Does this ever get to zero?
Nope.
No. So one formula you can use is the amount you start with. You could do 1/2, and then up here you're going to have t. This is a really bad formula, but it's easy enough to convert. You'd have a t there, and what you would do is you want this exponent to be 0 for 0, you want it to be 1 for 70, you want it to be 2 for 140, and so forth and so on. So you divide it by 70. So that is one formula that you can use for half-lives, but it doesn't tell you the percent change over time. So it's kind of a little bit of a messy formula. You want to do review work? Let's do review work. Ready? If I want to change this, I really don't need that part. I just need the 1/2 t over 70. And I want to change it into e to the rt. In other words, I want to solve for r. How do you do that? What would you do to both sides? You would ln. So if you ln both sides, the power would drop down out front. I actually could ignore the t on both sides because I'm not interested in the t. I'm actually interested in the r and its relationship to that 70. So I'm going to write this as 1 over 70, ln of 1/2. This side over here, ignoring the t, what would you get? R. So if I let r equal 1/70th of ln of 1/2, that would be its rate. All right, so that's one way of looking at it. Let's look at it a different way. We can also look at it this way. A equals per. And see what happens. So the amount after 1 half-life, if you started off with 200 kilograms, A would equal 100. So I would put 100 over here, 200 over here, e to the RT, and T was 70 years. So after one half-life has gone by, you go off from 200 down to 100. How do you, that's 70T. Noise bugs the heck out of me.
Somebody's knocking on the wall.
Yeah, it's 70R. I'm replacing T with 70. All right, how do you solve for R? You divide by 200, you get a half. And you get e to the 70R. Then you ln both sides, and you get ln of a half. Equals 70R. And R is equal to ln of a half divided by 70. So they come out to be exactly the same answer, which is kind of cool if you think about it. So whether you use the 1/2 version or the E version, I highly suggest you use the exponential version rather than the half version. It describes the rate better than anything else, which is more important for higher math anyways. Okay, so for example, I wonder if I can remember what it was. Maybe it's in the book.
Did you even make it a beat?
Well, I'm trying to use one that's actually realistic. If I can find it. So I don't have it in this book, I don't think. Oh, no, there it is. Carbon 14, 5,715 years. Of C14. The half-life of carbon 14 is 5,715 years. Carbon 14, carbon is, what's the, anybody know the? 12, right? So what's carbon 14?
2 extra neutrons. Well, right?
Electrons. I thought it was electrons, because you
No.
can't lose a proton and neutrons.
Yeah.
Well, you can gain electrons. It is electrons because
I hate chemistry.
the atomic number, which is originally 12, will always stay 12 because that's the protons inside the nucleus.
Alright,
But
so
the
14 would be
Because
Electrons
protons,
would-
you can change the number of neutrons. That makes it.
No, you can't.
Are you sure?
I'm pretty sure because all molecules gain electrons.
I always thought it gained 2 electrons and then it
They
lost
gain
it.
two.
Yeah, it gains 2 electrons. This is called an isotope. Isotope.
Look at it
And the last time I had chemistry was 1985.
You old.
Yeah. So knowing that it's 2 electrons, that takes a little bit of thought. All right, so if the half-life of carbon 14 is 5,715 years, how old is burnt wood that contains, I can't spell today, contains 15% of C14 it should. What's the only thing that absorbs carbon 14?
I'm guessing wood.
Wood. What else?
Paper.
Paper is wood.
So yeah, way paper still.
Bone.
Bone. Anything. Plants, animals,
Yeah,
anything that's
organic.
alive will absorb carbon 14. Rocks do not absorb carbon 14 since they're not alive. So they know how much carbon 14 is in a log that you just chop down and stops, growing. Once it stops growing and absorbing materials, it stops getting carbon 14. So if they can find wood that only contains 15% of what it should, you should be able to date it. All right? So how do I start this? I'm leaving off a few of the pieces and leaving big holes that you have to fill. So what should I fill first?
How much you started with?
I have no clue. It just says what it should have. I don't know what it should have, not off the top of my head. But how did I start all the other problems? What was the first thing I found? No matter what, you should always aim for
Right.
the rate. You have to. So you start off with f of t equals, the book will switch it over to a sub 0, and a sub 0 just represents initial amount. And over here they might put a. But ERT you can keep the same. They sometimes change that to K, the R, for growth constant, growth decay constant, that type of thing. But they're all exactly the same. All right, so do I know a sub 0? Make up a number then. What would be the easiest number? Okay, easy in terms of percent. 100. So you had 100% of the material on this side. How much did you have on the other side? 15. So if you started off with 100, you'd end up with 15% of it. E, I'm looking for R. What's T?
5,715.
5,715. And then solve for R. First step, divide by 100. Take a guess what this side turns into. 0.15, which is the decimal representation of 15%, equals, e to the 5,715 R.
And you put ln.
Ln both sides, so you get ln of 0.15,
And then you divide by 5,715.
and divide both sides by that 5,000. What kind of answer should we get out of here?
A negative number.
Why?
Because it's a half-life, so it's going down.
That and why by the calculation though?
Because
Why is it
it's an
negative?
ln of a decimal.
Well, so ln of 1.5 is negative?
I don't.
It's a decimal over, like, divided by a huge number.
No, the huge number doesn't matter. See, this is a positive value, so the only way to get a negative number is the top to be negative.
Cause you have to raise it to a fraction in order to make the decimal.
I was hoping you would just say the graph.
Um,
What's the graph of ln look like? Where does it start?
Oh.
It starts down here, right?
Yeah.
And it hits this point. What's this point? 1, 0. And then it grows really slowly. So anything between 0 and 1, the answer is going to be negative. It's down here. All right, so this is approximately negative
0.00033.
7 of zeros?
3.
Okay.
Lots of zeros. And the mistakes that people make, zeros. All right, that gives you the first half of the problem. How do I find the second half of the problem? How do I find out how old it is? Oh, we actually did 2 parts. No, shoot.
Oh, no problem.
Shoot. We made a mistake. Where's the mistake?
I don't know.
If you started off with 100%, after 5,715 years, how much should you have ended
it's
up with?
supposed to be 50.
That's supposed to be 50. So this is 50. This is 0.5. This is 0.5. This is 0.5. It's still going to be negative. But what is ln of 0.5 divided by?
It's the same thing, but the 33 is actually 1,2.
It's the same thing with the 3. That's not the same thing.
Negative
It's negative 0.00012. The same thing.
The answer is always 4.
That's good. 47.
Oh.
47.
That was always 4.
All right. So how do I find out how old this is? I had the setup for how old it is, except for a few differences. It would still be 15 is equal to 100 e to the
Negative
That thing.
0.000.
negative 0.00012, and then t goes here.
You're going to divide by.
Now we get that 15% is equal to e to the negative 0.00012t.
You go to L.
And ln it and divide, and you're going to get t is equal to ln of 0.15 divided by a negative 0.00012. I don't know how old this sucker's going to be.
It is
Since I made it up.
15,809 years.
Wow, it's pretty good.
Seems accurate.
Yeah, it's semi-accurate. It's not perfect. But it does prove certain things. Have you ever heard of the Shroud of Turin?
What?
The Shroud of Turin. It was supposed to be the cloth that Jesus was wrapped in, and they found it with this image of a person on it. And a lot of religious people thought it was the actual shroud that Jesus died in.
Maybe it was.
And what they did with the shroud is they did this carbon-14 dating on it and found out it was only 800 years old. So someone 800 years ago messed around with a cloth and painted or somehow got an image on it of a person and then tried to push it out there as a relic. Religions do that all the time. Hey, there's a relic. It's kind of like the toast that comes up looking like Jesus. Hey, there's Jesus on toast. Have you ever seen those news stories?
Yep.
Weird people. They see images of.
I've seen burnt toast in it.
I see bunny rabbits in clouds.
Found Jesus on my alphabet soup.
In my alphabet soup. Alright, so that's Half-Life and population growth and all that fun stuff. What's another good one?
I'm gonna tell you that. I'm gonna beat you with a
Ooh, Newton's law of cooling.
Oh, Newton. Great.
This one's not too bad. I mean, it's not perfect, but it's fairly close.
I haven't eaten all day.
You guys just jacked all class.
Yes.
No, we did last semester too.
Wonderful.
This is how it is.
Country didn't like it, but we passed.
Newton's law of cooling. Let me describe the pieces.
Whoa.
If I can remember them.
What was it, T? There's a C.
T0 is your initial temperature. C, if I remember right, is... Oh, no, wait. T0 is your room temperature.
What are they?
C is the temperature of your object.
Whoa. Oh.
And T and K, of course, are the constant and object room. And this takes away from it, eventually it goes to 0. Okay. So let's say you have a turkey. How high do you make a turkey? About 170 degrees, I think it is. About 170 degrees. So you cook it until it's 170 degrees internal temperature. And you take it out and you set it in a room that is 70 degrees. So obviously the turkey's eventually going to lose heat and cool down. All right. So one thing you do is you find out its temperature after a certain period of time. So it comes out of the oven at 170 degrees after, let's say, 10 minutes. It's down to 130 degrees. So it lost 40 degrees of its temperature. All right, so we should be able to plug things in and find out junk. So, do I know T for any of this? T being the final temperature, or the temperature after a period of time.
Yeah, you want the final one to be 70, don't you?
No, that's room temperature. I don't want it to get there. Have you ever eaten a turkey at 70 degrees?
I don't know.
Cold.
It's alright.
Yeah.
Pizza at 70.
So let's get it down to 130. So you put 130 here. Your room temperature is 70. Your turkey temperature is 170 minus 70.
So
E to the K times.
T.
Now, if you do T in minutes, T is always going to be in minutes. If you change it to hours, T is always going to be in hours. I highly suggest you stick with minutes.
So it's
But as you solve for the rest of the problem, T, you can't change it to something else. It has to stay in minutes. All right, so this becomes, what would you do first?
subtract.
Yeah, subtract those.
You get 100.
And while I'm at it, move that 70 over too.
Subtract.
So this becomes
It's going to be 60.
60 equals 100 e to the k, 10k.
Then you're going to.
And then we're back to the way we're doing it. Divide by 100, you get 0.6. E to the 10k. And you get ln of 0.6. Divided by 10 is equal to k. Positive or negative without calculating it? negative, because it's ln of something between 0 and 1. Which also tells you it's a decay. So k is equal to negative
0.051.
0.051. Alright. How long until it gets to room temperature, since you like room temperature turkey?
Yeah, Joe.
Ugh. How would I find that out? Well, T then would be,
Refrigerated.
if I wanted it at room temperature, what would the big T at the far left equal?
B70.
Be 70. I want room temperature is equal to, well, room temperature plus, well,
Can you just put
170 minus, well, room temperature, e to the
negative 0.051.
51, and then T. Oh, I don't need that last parentheses.
So
Right.
left side's going to be 0,
Equals
100.
e to the negative 0.051 T.
So 0 equals E.
Before you go any further, can you solve this?
You can't take an ln of 0, can
Well, that doesn't make sense, but it also doesn't make sense to have an exponential function equaling 0. Because exponential functions get closer and closer, but never ever touch. So this estimation of the temperature cannot find exactly when it's going to reach 70 degrees. So what do you plug in? 1. 71 degrees, and find out how long it gets to there, and then 70 degrees would be maybe a little bit longer, not much though. All right, how would you solve?
you? Divide by 100.
So this would be 0.01. I hope it doesn't take too long. But you definitely cannot get to the same temperature using this formula. It's better for temperatures that are above the room temperature. What's this give you for T? Just curious.
90.3.
So if you wait too long, your turkey's going to be totally cooled off. Hour and a half.
So about an hour and a half before it gets to room temperature.
Yeah, so more than likely it'll cool to 130 degrees quicker than 10 minutes, because I don't think it takes that long for a turkey to cool down.